7. So I'm Sudipto Das from Microsoft Research. I'll be chairing this session. So we have 5 talks here, 20 minutes for the first 4, 10 minutes for the last one. We'll keep a little bit of time towards the very end for questions, and I'll be monitoring that. So the first talk would be query-based workload forecasting for self-driving database management systems. It's a work coming out of CMU, and the presenter would be Linma.
All right. Thanks, Sudipto. Hi, welcome. I'm Linma from Carnegie Mellon. So today I'm going to present our query-based workload forecasting framework for self-driving database systems. And this is a joint work with my colleague at Carnegie Mellon. So database systems are very important for many data-driven applications. However, they are often very complex systems that require human expertise and labor to manage, which is an expensive process. So the question is, if our society right now is building self-driving cars to reduce the cost of driving, then why cannot we build self-driving databases to reduce the cost of database administration? But this is not entirely a new topic, because the question here is, how do we do it here to make it really work or work better? Well, I like to first draw some inspiration from self-driving cars. So what do you got there? Basically, typically you first have a perception component where you are going to use radars and cameras to monitor other vehicles and pedestrians on the road and predict where they are moving to. And then you'll have some actions, such as turning steering wheel, and then you'll have a planning component to decide a sequence of action to get to where you want to go, given the road perception. But it all starts with the ability, with the first component, to observe and predict. Well, without that perception component, instead of getting to where you want to go, you probably can only find out the dead people you ran over from behind. So we contend that for a self-driving database, the first step is also the ability to predict, or to observe and predict what workload you're going to get in the future. Well, this is very important for a database system because there are certain optimization actions in a database system. For example, building new indexes or moving data between different partitions or scaling resource up and down in a cloud setting. Those actions are too expensive to apply after you already observe that the workload has changed and requires those optimizations. In that case, that could cause resource contention and may actually slow down performance of the system. Of course, in order to apply those optimizations proactively, besides the workload forecasting, you also need other components. For example, you need planning component, observation component to decide what optimization to apply and how to monitor the effectiveness of those optimizations given the workload forecasting. But that's not what we are focusing on today. Today, we are going to focusing on the workload forecasting part. Now, how do we define this problem? Basically, workload forecasting is the ability to predict when, how many, and what queries will arrive at the database system at a given future time point. And beyond this, there are also 2 very important concepts. The first is how far into the future you want to predict the workload. For example, you could predict what workload will look like 1 hour from now, or you can try to predict what a workload will look like a week from now. That's what we call prediction horizon. The second is at what granularity you want to predict the workload. You could predict the workload at per minute level, or you are trying to predict what the workload will look like at per hour level. That's what we call prediction interval. And a good workload forecasting framework for self-driving database would have 3 goals. The first, it needs to achieve good prediction accuracy on different combinations of prediction horizons and intervals. Second, it needs to capture the major patterns for database applications, which I will explain in a minute. Third, it needs to achieve good balance between cost or overhead versus the accuracy of the prediction. So there are a couple of few challenges here. The first is that it needs to support a dynamic workloads. In order for a self-driving database to use this forecasting to optimize itself to improve the performance, this framework has to be integrated into the system in an online fashion. And it has to be able to capture the patterns of workload as well as adapt to the changes of a workload with a relatively low cost. The second thing is it needs to support large query volumes. So for the purpose of this project, we collected the query traces from 3 real-world applications. And for all of them, they execute at least millions of queries a day. And there's too much overhead, so that it's not possible that you record all those million queries and build forecasting model for each individual one of those millions of queries. The third is it also needs to support different arrival rate patterns. I'll give you 2 examples. First, I'm showing the arrival rate in a bus trapping application we collected over time, query arrival rate. Basically, there's clearly a diagonal or cyclic pattern where there are more queries during the daytime and on weekdays than other time. But in another example, which is a graduate school admission website, workload trace we collected, there are clearly two growth and spike pattern that happen only two times a year before the admission deadline, December 1st, December 15th. And not only different workloads could have those different patterns, but also within a same workload, for different subset of queries, there could be different patterns exist simultaneously. So efficient workload forecasting framework have to handle all of this. With that, I present our query-based workload forecasting framework for the database system called QueryBot 5000. It has three components, a preprocessor, a cluster, and a forecaster, which I will go over one by one. And the output of each component is going to be fed into the next component as input. Cool. Now, the first component, preprocessor. So I just mentioned that modern database system could execute millions of queries a day, and it's not possible that you record all of them and build forecasting model for each of those million queries. So there has to be some sort of a compression. Well, luckily, the first property we can leverage here for database application is actually the query language it is using, SQL, which is a very structured query language. So if we extract templates out of those SQL queries and then group queries that map to the same template together, then this can reduce the number of queries we need to monitor while maintaining important information of the workload. This is because queries that belong to the same template will likely to have similar performance impact to a database system. I'll give you an example. For example, here I have a simple select query, select star from foo, where ID equals to sigmod, and then we'll just extract all the constant parameters out of those SQL string, and then replace sigmod with a placeholder $, and this essentially would be the template, or essentially converts the query to a prepared statement. And we are just going to group all queries that belongs to this prepared statement together. And of course, in order to keep track of the distribution of those parameters, you also need to keep certain number of raw samples for each template. We also do a simple semantics equivalence check. For example, a query selecting column A and B from table is the same as query selecting column B and A from table. So these are all conservative heuristics without too much deep insight, but they are simple and stable. So with this component, we have already reduced the number of queries we need to monitor in the system from millions of queries per day to a couple thousand of templates. So this is good. I mean, lots of reduction. This is promising. However, as we found in our later experiment, if we want to use some complex time series analysis model to predict the arrival rate of queries, then it would take a couple minutes to build a forecasting model for each individual query template. So in an online fashion, this is still too much overhead. We need to further reduce the cost down. Now, here comes the second component, a clusterer, which is going to cluster similar queries together, or query templates together, to further reduce the cost. Well, in terms of clustering, then probably the most important thing is what is the similarity metric you use for clustering. So in general, there are three candidates, a physical feature, logical feature, and arrival rate feature. Physical feature is basically the runtime metrics you are going to record after you execute the query. For example, you could record the number of tuples read, number of tuples write, or the latency of the query, and that could be your feature. So there are definitely lots of information in this physical feature, but the problem is, for our purpose of building a self-driving database, if the database decides to apply some optimization, for example, build a new index, then the number of tuples read for some queries will change. Then your clustering would be invalid. I have to redo this clustering all over again, which incur unnecessary overhead. So this is not very suitable for our purpose. The second is logical feature, which is basically going to be the information you extract from the logical composition of the query or the abstract syntax tree. For example, you could record the type of the query, column referenced, or number of joins, or other keywords. Well, this is definitely independent of physical design or configuration of the database. However, as we found in our experiment, there are not enough information in this kind of feature to group similar enough query together. So the quality of the clustering is not good. Well, the second option, a arrival rate feature, we can think of the problem this way. If our final goal is to predict when and what query will be executed in the future, then why not we directly group queries that have similar arrival rate history together? And then we just need to build one focusing model on the average arrival rate on all the query templates that have similar arrival rate feature, and then represent the pattern for all of them. So for example, here I could have an arrival rate history for a query template, let's say, and then I will just do some sample timestamps throughout this history, and then extract the arrival rate at those timestamps out of it, and then that would be my arrival rate feature. We found that's actually pretty useful in our case. So let me give you a concrete example. So here, I'm showing you the arrival rate of the top 3 query templates in the bus tracking application in the largest cluster according to the time arrival rate history clustering. So we can here we can see, even though those query templates would have a different absolute volume, they all have the similar diagonal cyclic pattern. So we are just going to group them together and only build one focusing model on the average arrival rate for all those query templates to represent their pattern. Of course, in order to keep track of the absolute volume, we also need to keep track of the ratio between the volume of those templates and then cover them back later. So here I want to show you a little bit of the effectiveness of this component. I'm showing you the coverage of the largest clusters in 3 different workloads. And on the y-axis, according to this arrival feature clustering, and on the y-axis, very important, I'm showing you the ratio between the volume of the largest few clusters against the total volume of the workload. On the x-axis, I'm showing you the number of clusters for the measurement. So here we can see that if we just take the largest 5 clusters of each workload, they already cover more than 95% of the total volume of the workload. This essentially shows that a few large clusters already exhibit major patterns of the workload. So we are just going to build the focusing model for each of the very large few of them. And we also use an adaptive version of online DB scan algorithm to handle the changing of those patterns, but I will skip the details today. Now, lastly, the third component, forecaster. After we use the first 2 components to reduce the cost, finally we are going to predict the arrival rate pattern of queries in the future. So for this, we just investigated a couple of different models in the time series prediction literature, and there are 6 of them. And we chose those methods to investigate because they cover different properties in the space, namely whether it's linear or nonlinear, whether it's used a notion of memory to remember the previous input, or whether it's used kernel method to achieve nonlinearity. So in a nutshell, we found that those different models have different properties, so they work well in different scenarios. So one way in machine learning literature to solve this problem is that you use an ensemble method to combine the power of different models together. So we we investigated different combinations of those models, and we found out that if we take the average prediction of linear regression and RN, recurrent neural network, that would achieve the best average prediction accuracy in most of the cases for all the 3 workloads we have. So I want to give you intuitively how the forecasting perform in this component. So here I'm showing you the prediction results in the bus tracking application for 2 different prediction horizons, 1-hour horizon and 1-week horizon. So here we can see that predicting the future an hour from now is definitely much easier than predicting the future 1 week from now. But the thing is, they all capture the major diagonal cyclic pattern of the workload. This is important for a self-driving database because for a self-driving database, you do want to prioritize the configuration of the database towards the query to be executed in the near future, the longer run, because they're going to affect the performance of the database soon. For the workload in the longer run, it's okay that you capture the major pattern or magnitude of the workload. So that is good. However, if you remember from the beginning of my presentation, there's another common database pattern called growth and spike pattern, which is commonly seen in a mission website or a Black Friday shopping website or other things with a deadline. So how do we perform in that scenario? Well, this ensemble method doesn't work. The reason is because the 2 underlying models for ensemble method, linear regression and RNN, they are all parametric method where they are going to train certain weights as a function approximator to a training stage to predict the future arrival rate. However, for example, in this admission website, this growth and spike only happens 2 times a year before the admission deadline. So there are not enough training data for the model to learn those weights. But luckily, we investigated another model called kernel regression that can actually help this problem. So kernel regression is a non-parametric method, which means there's no weights, no training stage. You're just going to remember all the input and output pairs in your training data. And at the inference time, it's going to do a weighted average of all the outputs in the training set according to the distance of the data point to predict against all the data points in your training data set. So with this, it can capture this pattern with even only a limited data points before, as long as it has seen similar ones before. However, this method does not generalize well with the data point it has not seen before, so it does not have a good average prediction accuracy. So eventually, we use a hybrid method to combine the power of them together again. So in this hybrid method, we are just going to compare the prediction result of kernel regression and ensemble. And if kernel regression has a much higher prediction result than ensemble above a threshold, as for example indicated in the red region here, we are going to believe kernel regression and see there's a spike here and use that result. Otherwise, we are going to use ensemble. So this is a conservative approach. There are definitely more room for fine-grained improvement, but it already helped us to capture this important common workload pattern while maintaining a good average prediction accuracy. So at last, I want to show you the effectiveness of our forecasting in terms of helping the performance of a self-driving database in an example. So here I'm picking automatic index building, but we need to note that we're not trying to improve the algorithm of online index suggestion. Now we are saying this is the best application for forecasting, just one application we pick to show the effectiveness. So here we integrate our framework QueryBot 5000 with MySQL, and we are going to start to execute a workload with only primary indexes without any secondary indexes. And then we are going to use the same canonical index suggestion algorithm to build 20 indexes in total in 2 different settings. And the only difference lies in what is the input you use to the index suggestion algorithm as the representation of the workload, whether you are using the forecasting result or not. So I'm comparing 2 settings. The first is a retrospective setting, where we are going to build all indexes at once, secondary indexes at once, before the execution of the workload, and using a sample workload from the whole query history. This is mimic as an input to the index suggestion algorithm. This is mimicking a canonical DBA prepare a sample workload and run a tuning advisory tool setting. In the second predictive setting, we are going to build indexes one at a time at fixed intervals using the forecasting result of our framework. And in this case, it's going to build indexes for the queries to be executed in the future, or next few hours. So here's the result. First, I'm showing you the retrospective setting. Here, the performance of retrospective setting is relatively stable across the duration of the experiment because it already built all the secondary indexes before the execution of the workload. So at the predictive setting, I'm going to use these dotted vertical black lines to indicate when we build each new indexes for the workload to be executed in the near future. So here's the result. At the beginning of the workload execution, it is 80% slower than retrospective setting because it does not have any secondary indexes. But at the end of the workload, it achieves 20% better performance, even though build the same number of indexes as a retrospective setting, because it is recommending the best indexes for the queries you are going to execute in the near future. This essentially shows the effectiveness of what workload forecasting can bring. So before I wrap up, there are a couple of few takeaways I want you to remember. The first is we build a query-based workload forecasting framework can achieve good prediction accuracy on different combinations of horizons and intervals for self-driving databases. Second, we reduce the cost of forecasting with minimal loss of accuracy using 2 different techniques, query templatization and clustering on variety features. And third, we use a hybrid forecasting method to capture the major database workload patterns as well as maintaining good average prediction accuracy. So this essentially serves as the first step of our effort towards building a self-driving database system. With that, that's all I got. I'm happy to answer your questions. Thank you.
So we'll have to repeat the questions for the mic. So why don't you take this far away from me?
Oh, okay, sure.
So why don't you take the question and repeat it?
Sure.
So, 2 clarifying questions. So, one is, you said for your, when you compare your focus sample to the sample base,
Sure.
the default option,
Sure.
what is the sample strategy?
Oh.
If you give a uniform random sample, that's very hard.
Yeah.
So that's one. The second one is essentially how do you take the cost of building the index, the time to build the index into account? It depends on the size of the data. So unless there are 5 indexes that should be built now, there could all kinds of system constraints.
Sure.
And also,
Yes.
if their arrival rate is the same,
Yes.
cost of building the index would be vastly.
Yes. I totally agree.
Just summarize and repeat.
Oh, sure. So the first question is, what is our sampling strategy here in the retrospective setting? So it, like you said, is indeed a uniform random sampling. So yes, sure.
That's not a fair one.
Okay, but the point is that if you want to use some more advanced sampling strategy, that essentially kind of like you are implicitly doing the forecasting. Basically, let's say you want to sample the workload in the near latest time with more priority than workload in the longer run, then it's kind of like you are prioritizing this part. It's kind of like doing a prediction.
Sure.
Right.
I think that's what I'm saying. I think there are issues such as normal, you take into account what I told you.
Sure.
The cost of building that index,
Yes.
the benefit of building that index, and the arrival rate.
Sure. So and also so the second question is whether we are considering the cost of building indexes. So in this experiment, we consider the benefit of this index could bring, as well as the cost of maintaining these indexes. But in our specific strategy we use here, we do not consider the cost of implementing the index itself. But I would definitely agree that in a more thorough or principled strategy, we definitely need to consider that. But for the purpose of this experiment, we're just showing the result of forecasting. We don't have.
If it is an online strategy that has to be taken.
Yeah, yes. Actually, we are working on that right now. Yes. Thanks for the question.
Hi. What is the concept for sequences of queries that arrive together? So I'm not sure if it covers it, or if you will need to change the templatizer, or to change the similarity function such that it's not cosine similarity but dynamic term warping.
I'm not sure.
Sequences of queries
Sequence of queries arrive
that
together.
arrive at the same time. Yeah.
Uh-huh.
So what is your concept for this?
I'm not sure I really understand the question. Basically, if the queries arrive at a similar time, we are going to think they belongs to the similar cluster. And the point of this project is not to predict what next query will arrive after the first query has arrived. It's going to predict arrival rate of queries at a higher level, like per minute, per hour.
Yeah, yeah.
Within this minute, how many kind of this query arrive?
But if queries, I don't know how to say it. If queries do not, like for example, take 1 minute between each other and you have a sequence that arrives commonly,
Yes.
if you do a sample, it is possible that they do not go to the same cluster.
Yes. Yes.
Yeah.
Yeah, I mean, if you want to do some fine-grained optimization based on the sequence of queries and their relationship, you can also do that as a separate. But this only focuses on the total arrival rate of queries.
Okay, thank you.
Yeah, but nothing prevents you from
Yeah.
combining that optimization.
By the way, thank you because I think it's a very necessary work. So good.
Thanks. Yeah.